Okay. As long as none of y'all are too bright, I think you'll stay up near the light. Did I say that? I don't believe so. No. Thought you were leaving. I heard that was later. Okay. Slideshow. And I recorded that, by the way. All right, here we go. Jackets. All right. I think this is where we left off. Before we get started, any questions? And again, I'll say again, I apologize for not having the test finished. I'm pretty sure pretty close to half, and maybe a little more than half of it done, but I just ran out of time yesterday. And when Matt came in, he went just over half, so everything's just over half now. All right. All right. No questions, and hopefully Monday I'll have the test ready. I'm sorry it's taken so long to get it typed, but I really missed the 2 days last week that I had to be out, and so it threw me way off. Okay, what we were talking about last time was vector-valued functions, okay? They considered a particle in R3, that's three-dimensional space as we understand it. We talked about how it looked. Here is how it's represented on a graph. Now again, this is a three-dimensional graph, a two-dimensional graph representing three-dimensional space. So it's hard to tell which direction this is going. The indication here, since the graph is in front of the z-axis, I think it's somewhere here in this octave that's out here, but it's hard to say for sure. But at time, it doesn't have to be time, but whatever T1, at T1, this is the value of that displacement vector R. At value T1, that's your displacement vector. T2, it's here. Now, good crowd today. Jonathan's here. What's that? Yeah. Okay. At T3, your vector is over there. And at some future time, R of T is over here, and every one of these, the coordinates from this point, R of T, of this function, this vector, R of T, is x of T, y of T, z of T. This would be x of T1, y of T1, z of T1. This would be x of T2, y of T2, z of T2, and so on. And for any old point, time, or value T, R of T is x of T, y of T, z of T, and it is a vector function. I think what happened is when I opened the windows, that probably increased the temperature a little bit, and now this is blowing colder air faster. So maybe the window was a bad idea. I don't know. It's freezing here. Okay. Now here is the path of the particle. In good old two-dimensional space, this wouldn't even be a function, would it? Because it looks like it might violate a vertical line test somewhere here. But it's not. This is a vector function, and as long as at any t, that could be time or whatever, at any t there's only one value of that function, that is a vector function. It can't be at t1, it can't be here and there at the same time. Okay? So therefore this is a vector function. Even though it curves around, it can do loop-de-loops, it could overlap itself, that's perfect. Well, yeah, it could do that. At any time t, it can only be one place. Okay? So it can go around the surface. But at any time, it's only at one place on that surface. So this is indeed a vector function. That's how it looks. That's what we're dealing with. Any questions on that? Now, it says here, more generally, a vector value function is any function R of t in this form that we showed last time. That was this slide. this is a three-dimensional space vector. You can have n-dimensional space vectors. You just can't draw them, especially on a two-dimensional slide. I can't even visualize anything beyond that. Now, that vector value function in this form here, should have left it up a little. This is on page 689 in the new text, and the older one that's I swear. Okay. Now, in most functions, okay, this represents a function. What is your independent variable? T, exactly. X, Y, and Z are no longer independent variables. They're kind of intermediate variables. Your dependent variable is your R, okay? R depends on T. But X depends on T, Y depends on T, and Z depends on T. And R does depend on X, Y, and Z, but they all depend on T. So the only really, truly independent variable here is your T. R is your dependent variable, and the X, Y, and Z's are sort of intermediate variables. They depend on T, but R depends on them. So they're kind of in the middle. And I guess you could have several layers of them. Okay? Now, that independent variable, T, is also called a parameter. All of the other functions are based on that parameter T. Okay? And that's why we talked about parametric equations in the last chapter. Okay? And even the one before that, too. Okay. Now, in this representation, these are the components of the vector, x of t, y of t, and z of t. They're variables because the vector's a variable, but at any one value t, those are components of that vector at that value t. Okay? Now, guess that's enough. When you represent the vector in vector form such as this, then what you're doing, you assume standard position for a vector, the initial point is the origin, and then draw the vector from there. Where do you draw it to? Well, that x, y, and t that are components of this vector, when the vector is placed within at the origin, they are the coordinates of the point on the curve where the vector intersects the curve. And so they're components of a point, coordinates of a point, components of the vector. Okay. Not to make hopefully too big a deal about that. So let's look at a couple of illustrations goodness gracious, they give here. Here is a vector. Well, let me get my pen activated. Okay. R of t. This R of t is a vector function. That vector function is t squared for the x component, e to the t for the y component, and 4 minus 7t for the z component. Okay? Now, what is the domain of that function, vector function? And by the way, this is a vector function, so that I'll draw as a vector. It is a vector. Those are angle brackets indicating a vector. I'll also do that.
X positive.
Okay. What was the domain are the values for the independent variable. X, Y, and Z are intermediate variables. What's your independent variable? T. So from just looking at it, T would have no restriction. So we'll assume all real numbers unless the problem or the physical situation or something like that restricts it somehow. So for now, we'll say for that vector function, the domain is all real numbers.
It would be if T was in the denominator or something that would cause an issue or something like that.
Now say that again.
If T was in the denominator for one of these, like.
Right, yes, exactly. Then that would be a limitation. If it's under a square root, it's a limitation. It's an argument of a logarithm. That would be, so those are the things that you watch for. Now, I said that, but then they're contradicting this, and I think Cameron's answer is better than the book's answer. No, I'm sorry. You know, they say the domain here is R, which is one-dimensional displacement. And this is not a one-dimensional problem. Now, it's not all of space either, if that's what they're meaning by R, which I don't think that's what they mean. So I guess by R they mean, maybe that means real numbers. That perhaps is what it means. Not one-dimensional space, but all real numbers. And again, that's talking about T. So I think that's okay. I'm just not used to the way this book represents real numbers, but I assume that's what that means by that. All right, let's do another one here. Here is an R, this time of parameter S, but this S is the components of the vector R. It's the square root of S, e to the S, S to the minus 1. What's the domain of that vector R?
It can't be 0 because S to the minus 1.
Right.
And it can't be negative because of the square root.
Right.
So it has to be positive.
So it would be, yes, not equal to 0, but greater than 0. So they say the domain is equal to the set of all real numbers S such that S is, okay. I'm going to put it the way the book did. I usually don't include, yeah, I could have done it there. I'm sorry. Okay. All real numbers S such that, no. This thing, I hit erase, and sometimes it lets me and sometimes it doesn't. Okay. S is an element of the real number system, and that's what they stand for, the R. Okay. Most books use a fancier, different kind of thing, such that S is greater than 0. Not greater than or equal to, but greater than 0.
So S greater than 0 isn't really a complete answer there?
Yeah, any value. Now, one thing I did notice here, some books use a vertical line for such that. This book uses a colon. I've seen both of them use this, uses colon. So it's saying S is any real number as long as it's greater than 0. Now, what were you saying?
I was saying, so S greater than 0 wouldn't be a complete domain?
Yeah, you mean if you left off all the squiggly lines and stuff like that?
About the,
If you just said S greater than 0,
right.
I recognize that as being a real number S. So yeah, this is just how they say it in set notation, full force thing. Now, this one here that we showed here, they don't indicate there's any limitation since there's no dot at the end or at the beginning or the end. We assume it's going on in both directions. So we would assume that's all real numbers. This one, however, your S has to be non-negative for this and non-zero for that. So greater than. If that had been an S there, then greater than or equal to 0 here. If this had been an S here, that's S to the minus 1. instead of all S such that S is not equal to 0. All the others will be fine. So that's how we talk. But you're talking about the independent variable, the one and only that parameter. The terminal point of a vector value function traces a path in R3 as we see here. That is your path. The red, fuchsia, whatever you call that, that's the path, also sometimes called the curve. It's the path of the terminal point of the vector function. That's the path, okay? And generally it'll be somewhere in R3 in real life most of the time. Now, pure mathematicians, you'll get into R in space and float around out there some, but you know, most of us live in 3 space, and that's where we're going to stay. We refer to R either as a path or as a vector parameterization of a path, okay? Sometimes I'll refer to it as the curve, and that's sort of okay too, but curves are made up of points. Paths are made up of vectors. So that is a subtle little difference, but we'll keep running into it, okay? We'll assume throughout this chapter that the components of R have continuous derivatives, okay? Within their domains, I'll say, okay? Would you say that this has a continuous derivative? All of those? Certainly equals 0, that wouldn't be continuous there, but as long as your domain is greater than 0, then it's continuous. Within the domain, continuous derivatives. Okay. Sorry, I'm so clogged up. We've already studied special cases for vector parameterization, chapter 12 and so on. Recall that, and just as a reminder here, if you had a R of t, we'll go back to t, you can use any dummy variable there you want. I wouldn't use r again or x, y, or z again, but R of t equal to the vector x sub 0, y sub 0, z sub 0 plus t times some vector v. Okay? Goodness gracious. Cold. Now, what does that represent? Anyone remember? We touched on it in chapter 11. No, 12. Maybe 11 too, but I remember 12. Sorry. Damn, it's cold. Yeah, it is adding 2 vectors. And what's the result of adding 2 vectors? Okay, which basically represents a straight line. This represents the line that's parallel to this vector v, parallel to it, meaning that you just, well, I'll get back to that. Parallel to v, that's the only thing with the direction here. This is a vector going to one point, and then from that point, the vector v is added to that, so any multiple of v. So if v is really short, it might be there. If v is longer, it's there. If v negative, it's here. So this is a vector function of a line that goes through this point here. A line parallel to v and going through that point. Okay, that's we hit on that. I think it was the last chapter. Okay, the equations for a line. That's one way to represent it. Okay, now, as you said, this is a vector. It's a sum of 2 vectors. Yeah, vector here, vector here, vector there, sum of 2 vectors. And here is the component by component of that vector. X sub 0 plus t, what do they call A, this vector implicit here, this vector is represented as having components A, B, C. Okay? So that would be TA, Y0 plus TB, Z0 plus TC. Okay. Okay. The vector is vector ABC. Okay. Now back in chapter 11, we studied parametrized curves such as the plane curves in the plane in two space, R2, of the form C of t is equal to, now these were curves, C of t is equal to x of t, y of t. Now this is a place where it gets, to me, squirrely. Maybe it's really clear as day to you. That looks a lot like a, yeah, well, it's not, yeah. It is a point, but a variable point. This then is a curve. Curves are made up of points. Vector functions are made up of vectors, not points. So this could be describing a path that you would represent as a vector function. Then you would have angle brackets, okay, if you're referring to some vector C of t, okay, which would be the path. So the path is vectors, the curve that's along that path is usually scalars, okay, points, made up of points. And again, I don't want to make too big a deal of it, but here's what they say. The difference lies only in whether we visualize the path as traced by a moving point, C of t, that's what this represents, or a moving vector, the end of a moving vector, then it would be R of t. Okay. I don't know why they make a difference, but they do. Okay. Now, here's example 1. Well, let's talk about example 1 first, and then I'll show you the thing. Describe the path of R of t when this is, and this is a vector, so these are angle brackets, cosine t, sine t, 1. You describe that for me.
Well, Z is always 1.
Yeah, the z component is always 1. So if you pictured 3 space, if this were 3 space, x coordinate, y coordinate, z coordinates, then 1 up was where you're going to be living here. Everything is at 1. Now it can be back into the room behind us or out there or anywhere else. Z is equal to 1. Right?
And cosine is between 1 and negative 1 on the x-axis, right?
Okay, between plus and minus 1 on the x-axis. That's the x.
Sine is the same, but on the y-axis.
On the y-axis. And if you had just knocked the 1 in there, ended it there, and that was, what would that represent? Okay, where does cosine start? Let's start at t equals 0. What would cosine be? 1. What would your sine be? 0. So that would be some point 1 out here. Let's just say that's this is 1. So there it would be right there. Only we're going to be at 1, so we're going to be at the z-axis. So there's 1. 1, 0, 1. Okay? Give me another t. Pi halves. If pi halves, what's cosine? 0. So your x is 0. Sine is 1. So now we're out at 1 here. And here. And z is still 1. So how did we get from here to there? Was it a straight line? It's a curve. And you keep on curving, and curving.
Is it a circle?
It's a circle. That's exactly what it is. That is the, this is a circle at z is equal to 1. And that plane z is equal to 1. And that's how it looks. What's that? Yeah, and it'd be a unit circle. Radius 1 at height z equal 1. Okay? Now, I don't think they've scaled this too well because this should be 1, that should be 1, and that should be 1. It's really stretched the z out a little bit on it. Maybe because the other two are foreshortened coming out at us. You know, that's why it's hard to picture this in on a two-dimensional plane, a three-dimensional shape. But that's what you would have here. Now, what if you had let that R of t, as it tracks that circle, what shape would you have formed? A cone, exactly, or half a cone, because actually a cone goes plus and minus. Okay, very good.
Has a waist of a point.
Yes. Okay. Oh, and by the way, what are the limits for t there?
Anything between 0 or it's anything.
Anything. Plus or minus, it just goes round and round and round either direction you want to go. Just keeps going. So you would, yeah. You wouldn't technically call that a function in two space because wherever you draw it, the horizontal line test, vertical line test would fail. But see, in three space, as a vector function, it's perfectly fine because at any value t, you're only at one point. You may hit that point many times around, but at any value t, you only have one value for R of t. Good deal. All right. Now, a curve in R3 is often referred to as a space curve as opposed to a curve in R2, which is called a plane curve. And the trouble with space curves is hard to represent them on a two-dimensional sheet of paper or board. You know, they're kind of hard to see. So it all depends on your perspective. Okay? And this is unbelievable, but these are three graphs of the same space curve.
Just from different angles.
Looking at it from different angles. You're absolutely right.
Yeah, I guess that would make sense.
What's that?
That would make sense.
Yeah, and it does. Okay, but all right. Here the x, positive x this way, positive y that way, z's up like this. And it looks like it's coming out of the origin, probably hanging closer, a small x change, pretty large y change, very small z change. But then the x starts changing big time, y looks like it's decreasing. You can't really tell what it's doing vertically. Hard to say, but then it loops around and does this and that and that and that and that. Really weird looking shape. Same curve. And here's the curve, by the way. The R of t is t sine 2t cosine t. That's the x component. T sine squared t, y component. And t cosine t, z component. Okay? And this is only going from t equals 0 to 4 pi. Okay? So let's, certainly at 0, it would be 0, 0, 0. So that's why it's starting at the origin. Now let's pick the same point you did pi halves. Well, sine of pi is 0. So even though the x value came out here, it goes back to being 0, probably somewhere around in there. Cosine of pi halves would be 1, and that's why you're 1 unit out here. Okay? Then, by the way, 1 unit here, if that is pi halves, then this is 0. The x component is 0. Okay? If this is pi halves, and sine of pi halves is 1, so that would be pi halves, and cosine of pi halves is 0. Okay? Now, so at pi halves, So this is pi halves times 1, so your pi halves, okay? The y component is pi halves. X component is 0, y component is pi halves, z component is 0. And there you're right back, you're on the y-axis there, 1 unit out with x equals 0 and z equals 0, okay? So that's the pi halves. Let's go to pi. What would this be? 0. We can't get off 0 on x here, it looks like. So that's probably this one here. In between, it's done some wacko things here, but it's fine. The on this, by the way, would be a negative 1. So
times 0 is still 0.
yeah, it's times 0 is still 0. Yeah, that's why we don't see that. Here we have. Now we're at pi now. Sine of pi is 0 again, so we're back at not only is x equals 0, but your y is equal to 0. That's maybe this one back here. And what's your z equal to?
1 pi?
Well, negative pi. Negative pi. So that's why you're down here on the negative pi here. That sure looks too short for negative pi. So you keep on going like that, and you pick up the points and the values, and they do. Now, if we change our orientation, all right, ooh, goodness gracious, I've been not paying attention. Ashley has come in, which is fantastic, and Tony has come in, which is fantastic. I've got to find it. There you are. Okay, we're just missing Javon. Wow, almost perfect attendance. Way to go, folks. That should be 8 people. Yeah, excellent. So we change our orientation, moving y back this way, and x is coming out this way, z still up and down. Now we see a little bit better. It's going here, x is going, looks like it's going negative here. I didn't see that here. Should it look like it to me? Back to 0. Here z is, x and y are 0. And it curves all around, x equals 0 again, y is equal to, I'm guessing that's pi halves, pi, 2 pi, 3 pi, or something like that. And the z goes up, down, up. The next one would have been down. So that's what's going on here. Same picture, but it just looks very different here. And if we do it this way, that the x is going back into the board, positive y is this way, it sort of looks just like this, only almost flipped. There's a little bit of other subtle changes there. What's that?
You don't see any overlapping.
Right. Yeah, like you have here and a little bit here. And part of the reason for that, you have a different angle on x. Positive x it's still a 90-degree angle, but the perspective is very different. So, yeah, it's hard. The whole point of this is very hard to represent three-dimensional shape in two-dimensional plane. Hard, almost impossible to do. Okay? Example 2 describes a helix. So, let's see if we can do this first, this way. Describe the curve traced by r of t is equal to, I lost my place there, minus sine t, cosine t, t. All right. Now, here's how I usually will do something like this one. Because the t is kind of plain there, let's not quite meaning that P-L-A-N-E, P-L-A-I-N is what I meant. But let's sort of ignore this. What would this be describing? If these were your x, y's only, what would that describe? a circle again, okay? Now, the one thing that's different about this circle is it starts at a different location. When t is equal to 0, this is 0. Before it was 1 when it started as cosine t. So this is a 0. That's a 1, okay? So you would start over here then, 0, 1, and then as t increases, sign is now going negative, not positive, okay? So your sign would be going that way. So it would be going around like this, okay? But t is in here at z, and when t is equal to 0, you're 0. But as t increases, then it still forms a circle. If you look down on it, it would appear to be a circle, but now it would be rising like that, okay? And that's what's called the helix, okay? Think of it as a spring, a spiral, or something like that, but that's technically called a helix. Here is the representation of that. The projection on the xy plane, just your circle. And what circle is that? It would be this one here. And it would be going around and around like that. So it starts at 0. So, yeah, I think that's right. 0, 1, 0, x, 1 on y, and then it goes around and around and around like that. Okay. Oh, I'm sorry. Here's x. Starts here, and then goes around like that. But all the time it's going up. So if you looked at the projection on the xz plane, in other words, leave off the y, and you have a function that looks a lot like a sine function, negative sine function, because it's going negative here, positive here, and negative. Well, what's it doing on the yz plane? Then block out the x, and you're going, let's see, I could blow this up. I don't think I did I? Let me see. Ooh, yeah, that's the problem. I can't see it all there. Okay. Hopefully this won't be too bad of a representation of it. Okay. And then projection onto the yz plane is block out the x, and you have basically a cosine looking thing starting at +1 and then doing like this. Okay. So sure enough, that's what the looks like. In three-dimensional time to plot it onto a two-dimensional plane, this is what your helix looks like. Okay. Looks like it's really broad circle here, real tight there. It really isn't. It's just you're coming in from the back side and you don't see that advance forward. So that is going up uniformly, like these two show. It's just really hard to pick it out on the three-dimensional plot. Make sense? Okay. Now, I guess we should have worked those out ourselves. But it's a lot easier to look at theirs and say, yeah, I agree with that, rather than having to draw them yourself. All right, let's look at example 3. And again, this is going to be hard to do. I don't have enough room. Here's example 3. Parametrizing the intersection of surfaces. Parameterize the curve C, okay, obtained as an intersection of the surfaces x squared plus y. Let me blow this up a little bit. We can't see it all at once, but we can see, let's see if we can see as much as possible. Okay. Okay, we'll start here. Parameters of the curve obtained by the intersection of the surfaces x squared minus y squared is equal to z minus 1. That's this. What did we call this? Remember what we named that? 12.6. I thought I read your lips to say paraboloid. That's right. Okay? It's a paraboloid. Okay? Now, and let's see. Yeah, and they had both elliptic and hyperbolic. This is the hyperbolic. I thought I read your lips saying that too. Because looking at it from certainly down the y-axis, that's a parabola. Every intersection is a parabola. From the x-axis, every intersection is a parabola with it curving up. Okay? But looking down at it from the z-axis, if we did the traces here, you'd have a curve around here and a curve around there. That's hyperboloid. So a hyperbolic paraboloid. Very good. You know it's a paraboloid because two of them are squared, one of them is not. Any one of those is paraboloid. That's a hyperboloid. Okay? So, yeah. Now, our other shape here is, what would you call that? A circular, what do you call it? Cylinder, circular cylinder. Because your cross section here, when z is equal to 0, or any other value, is going to be a circle. Okay, x squared plus y squared is equal to r squared, 4 squared, okay, 2 squared. So it's a circle with radius 2, but then with z is allowed to go from minus infinity to positive infinity. That's actually a right circular cylinder. No top and bottom. Okay, now what we want to do is superimpose this on that, or vice versa, and talk about the curve we have as a result of that. Okay, now, we know you're going to have this radius of 2 everywhere, so it would be sort of fun to say what happens when x equals 2 and y is equal to 0, okay? Where would that one be? When x equals 0 and y is equal to 2, we know that's on that one as well. Where would it be here? In terms of where on z, and do that for several values that you know are going to be x squared plus y squared equal 4. So what does that look like? Okay. Whoa, that's not what I wanted to do. Okay, sorry about that. Okay, that's what we were looking at. This is one I meant to hit. Okay. Where those intersect, you put the cylinder down in the hyperbolic paraboloid, then the curve that you trace out is something that looks like this. Okay. At least in this representation, it looks a lot like a Mobius strip, but this is just a curve, but you get the general idea of that. Okay? Now, take away the shapes, and what do you have? Let me hit the right button here. And you have this kind of thing, just the curve, okay, without the shapes there. It's kind of hard to see what describes that, but sure enough, this is the shape you got. All right. Does that make sense? Now, what's really hard to see is if you were looking down the z-axis of this, what would that look like? A circle. It has to, because that's what this looks like. So, and all that's on the circle. It's just that you can't see the other components of it looking down at it. It would just be the circle. Exactly. All right. Any questions on that? I think that covers that. Am I going to ask you to be drawing these on test? I sure hope not. Okay, because I would hate to have to grade it. Okay. miserable. Okay. Now, they say parameterize the curve C obtained at the intersection of these two surfaces. Not drawing them, parameterize it. Okay? So, and they give you two different methods for doing this. So let's go back. Well, let's just get out of this altogether. And we've got to parameterize the curve C obtained by that intersection. Okay. They give you two methods to do this. I don't know which one of them you might prefer. It says first solve the given equations for y and z in terms of x. Now somehow I would not have chosen it to do it that way, but that's what they're suggesting that we do. Okay? See, my first inclination would be to solve it in terms of z. But why that's not a good idea is there's no z at all in this one. So that would not be a beneficial thing. You need to solve this in terms of either y or x. They chose to do x first. That's fine. So y is in terms of x. So solving for y in terms of x. Okay? Well, start with the cylinder here, and you get y is equal to, well, let's do it this way. Y squared is equal to 4 minus x squared, solving this in terms of y, subtracting x from both sides, x squared from both sides. Okay, that gives you y squared, and then take the square root of that. Y is either equal plus the square root of 4 minus x squared, or later he'll come back and do y is equal to minus the square root of 4 minus x squared. Okay? So you got the y as expressed as a function of x. And you can do the same thing, x as a function of y. Okay? Now, so they just say it plus or minus. I think it's best to do it. Now, this next equation, this one, frankly, I think it would have been far easier to leave it in y squared and then said that x squared minus 4 minus x squared, that's your y squared, right? Okay, is equal to z minus 1. So in other words, 2x squared minus 4 is equal to z minus 1. Okay. Yeah. And if you wanted to add 1 to both sides, which is what I was going to do, but I want to make sure they did it, that would give you z is equal to 2x squared minus 3. And that's what they got in the book. Okay. Now, it says, now introduce a parameter. Well, let's let x equal t. Okay? So, if x is equal to t, this is how you parameterize. X equal t. You get y in terms of x, z in terms of x, so let x be your parameter t. That makes the y equal plus or minus the square root of 4 minus t squared, and it makes the z equal 2t squared minus 3. Okay? There is your parameterization of that curve. Now, the problem is you got a plus or a minus. So you really have two parameterization, one with y negative and one with y positive. Okay? So you just do them separately. Thing together there. We do it. So basically your idea was use this to solve for either one. You could have solved for x as a function of y, and then plug that in here, and then found z as a function of that y as well. Let y be your independent variable t, your parameter t, and then go back and recreate. Sorry, my eyes are so dry. Okay. Now the second method, I don't know if you like this as much. It's, to me, is a little more abstract. Okay. It said, note that this equation here, x squared plus y squared equal 4, you could write in basically polar type units. Excuse me. Hard to breathe. If you know that x is equal to, what is your standard polar coordinates for x? X equal r cosine t, y is equal to r sine t. Well, you know your r here is 2, so that would be x equal 2 cosine t, y is equal to 2 sine t. Okay. Then express that. Now I said t. I tend to use theta, but they use t as well, so it's fine. There's nothing that makes t magical. They just like to use it. And that would be good for any value t. Excuse me. But they're letting t go from 0 to 2 pi and just make one trip around. Okay? Well, when you got that, then you just plug that into your z, and you've got another representation. So here you have x equal to cosine t, y is equal to 2 sine t, and z would then be equal to, and you can either go down and use this, or like we said, don't use that, I'm sorry, it's, use this one here and plug in what x is. Oh man. Right here, I would use this one. So let me, I'm sorry, I can't talk. Well, that's not what I wanted. Yeah, it is what I want. Okay. Here's what I'm going to do. See, this z minus 1 is equal to x squared minus y squared. Plug them in, plug them in. So z minus 1 is equal to 4 cosine squared t minus 4 sine squared t. So z is equal to 4 cosine squared t minus 4 sine squared t minus plus 1. So there's another parameterization. The first did it basically rectilinearly, the other did it sort of polarly, you know. Now, they don't leave it like that. They do some other adjustment to it. And how do they manage that? Well, here they use some trig identities I'm not sure you're all that familiar with. Let's just do this. 4 times cosine squared t minus sine squared t plus 1. Right? Now, do you happen to remember a trig identity that is similar to cosine squared t minus sine squared t? Any of you? I'm going to indicate how to get it. Of course, I know the answer, and that's what leads me to this. Does anyone remember what cosine of, let's call it r plus s is? Remember that one? Cosine r cosine s minus sine r sine s. Okay. Hopefully I haven't chosen variables that are hard to distinguish, but that's what it is. Now, let's imagine that these two are the same value. R is equal to S, and let's call that T. Each of those is T. So then this would be cosine 2t is equal to cosine t, that's cosine squared t minus sine t, which is sine squared t. Well, sure enough, there is an identity. This cosine squared t minus sine squared t is simply cosine of 2t. Okay? So then we can call this 4 times cosine 2t plus 1. I think that's what they got in the book. Let me find it. Yeah. 4 cosine 2t plus 1. And there the t is, again, limited to one time around 0 to 2 pi. Or any 2 pi time around. All right. Excuse me. Now, this is the illustration of what they did in the first one. Remember when I said they took the positive y and the negative y. And this is a part of the curve where y is positive, greater than 0, and then the second part is when it's less than 0, and you put them together, and that's what you got. So I think that's not much more you can say about that. Here is example 4. I'll blow it up for now, but we're going to have to come in and do some writing so it's going to lose its most favorable nature status here pretty quickly. All right. Parameterize the circle with radius 3 with its center P at 268 located in the plane. Parameterize the circle of radius 3 with its center P is equal to 268 located in the plane. And the first plane is that plane parallel to the XY plane. So that's your first picture there. Okay? All right. Sorry, I can't breathe. All right. The dead giveaway here is, in this first one, z is always 8. Z is always 8. Okay? Now, they showed the center being from 0, 0, 0 to 268. What they didn't show is the circle here, parameterize, let the vector here come along and describe that. That's going to give you your parameterization that you need. Okay? So you know the circle has radius of 3 and the center's there, but your That's going to trace that. Now, we did an offset of a line. The circle's not going to be a lot different from that, but a little bit. Let's first describe this circle here. How would we describe this circle down here? Radius 3 was centered at the origin. What would that circle be? Any ideas? Parameterize that circle right there. Okay. I'm going to have to shrink it to do it, and it's going to be harder to write. But here we'll go. This circle down here would be 3 cosine theta, or let's call it t, I think they do, 3 sine t. Okay, that's the radius going around the origin. Do you buy that? Okay. Now, to get that one up there, and by the way, your z down here would be 0. Okay? So the one up there would be, it looks like it would be 2 plus 3 cosine t, 2 plus 3 sine t, 8. I'm sorry. No, 6 plus, sorry, 8. 2 plus 3 cosine t, add the 2 to your x value here, add the 6 to the y value here, and add the 8 to the 0 value there. That, to me, looks like the parameterization of that circle offset up there. Let's see what the book did. 2 plus 3 cosine t, 6 plus 3 sine t, 8. Perfect. All right. However, how are we going to do that second circle? The one over here. Again, I would ask you, how would you parameterize this circle? Still got radius 3. But where does this circle live? In the what? 0 on the y. 0 on the y, and the rest of it on x and z. So that would be, this circle here would then be 3, where did I start? Cosine t 0, 3 sine t. Okay? And then you would add that. So this one up here at least appears to be 2 plus 3 cosine t, comma, 6, comma, 8 plus 3 sine t. All right, let's see if we got it anywhere. 2 plus 3 cosine t, 6, 8 plus 3 sine t. Got it. Changes the orientation and everything, but it's parallel to the xz plane. So therefore, the y is always constant at 6 now, and your it just varies with x and z. Does that make sense? All right. That is the last example in the text. Okay? So, we're finished with 13.1, except for the preliminary questions. I take it y'all want to do these or not? Okay. Let's clear the slide then. And we'll write on this one even though it has nothing to do with the picture, I don't think. Okay. Which one of the following does not parameterize a line? Okay. A. Now these are all vectors, this is R1 of t is equal to vector components 8 minus t, 2t, 3t. Okay, the B one is R2 of t is equal to, and they wrote it in a different format, but it's fine, t cubed I plus minus 7t cubed j aggravates me when it does that. Okay. Plus 3t plus t cubed k. Okay. That's the B one. Here's the C one. 8 minus 4t cubed, R3 of t, is equal to 8 minus 4t cubed comma 2 plus 5t squared comma 9t cubed. Okay. Now, which one of those does not parameterize a line? How about A? Yes, it is definitely, because everything's power of 1. Okay? All your t's are in the first order. That's going to be a line. Okay? How about B? Okay. Yes, it happens to be, because you could do a substitution, let u equal t cubed, and then that would be a line in with parameter u rather than t. So that one would still be okay. How about C? No, it can't, because you have different powers of the t, and you can't parameterize it with it. If u equal t squared, then you have the x and the z have t to the, or u to the 1 3/2 or something like that. You would just have an off power there. So we think the first one is going to be, which does not parameterize a line, C. Let's see what they say. See, this is 13. I'm sorry, I'm the wrong marker here. 13. Well, I gotta find it first. 13.1. C is the one that does not parameterize a line. Okay. Number 2. I think I'm going to erase this. Is that okay? I'm going. Sorry. Breathe. Okay, goodness gracious. Number 2. What is the projection of R of t, which is equal to ti plus t fourth j plus e to the tk onto the xz plane? Okay, what is the projection of that onto the xz plane? What would that give you? That's making the y 0. Because if on the XZ plane, y is 0. What does that projection look like? We'll use this XZ plane. There's X, there's Z. Well, this one has the same thing, but you see something in that. What does that look like then? It would be basically an exponential curve. Okay? It would be keeping close to the x-axis here, passing through 1 here, and going like that. Exponential curve up like that. Now, I don't know what they're going to do in the back of the book, if they draw that or just describe it to you. Let's see what they do. The curve is z is equal to e to the x, which is just what I was saying, because x is equal to t, right? And then this would be z is equal to e to the t, which is e to the x. And that is the curve that you would have there. And that's one straightforward way of doing it. All right, that was number 2. Any questions on that? Number 3. Which projection of, okay, let me go and erase this one too, because not that it's going to take up that much room, but just, okay. 3. Which projection of this vector, cosine t, cosine 2t, sine t, is a circle? Which projection of that is a circle? Second?
Onto the y plane?
Okay, onto the plane where y is equal to 0, is that what you mean? Yeah, and what plane would that be? The XZ plane. So they're stuck on the XZ plane, aren't they? Okay? That better be the XZ plane. Let's see what they say back here. The projection is onto the XZ plane. Good, they got it right. Good deal. That's number 3, I think. Number 4. What is the center of the circle with the following parameterization? I think I can get this one on here. R of t, this is the parameterization. Parametrization. I always put a ter in there, but it's parametrization. And they write it in IJK format, so this is minus 2 plus cosine t I plus 2j plus 3 minus sine t k. All right. What is the center of the circle with that parameterization? It's going to be a point. What would it be? Did you say negative 2? Negative 2, 2, 3. Positive 3. You got it. It's just the minus sine t has it going in a different direction, but it's just that. So yeah, that should be negative 2, 2, 3. That's the wrong one. Negative 2, 2, 3. Good for them. Okay, that was 4. Now let's do 5. I think 5 is probably going to need some more space. So let's clear that. How do the paths R1 of t, and that's going to be angle bracket cosine t sine t, okay. Got what you needed early, huh? So quickly.
I got all that I could and came back.
All right, good deal. Was it a pretty good show over there?
They just started the ceremony. There was probably close to 10 tables set up.
Yeah. Good.
They do
All right. Okay, we're doing section 13.1 preliminary question exercise. 13.1 exercises preliminary question number 5. How do the paths of this R1 and this R2, which is sine t cosine t, how do the paths around these 2 unit circles differ? Both of these are unit circles. How do they differ?
The Y and the Z are switched? I don't know.
Okay, it's all X and Y. We're not doing 3 space. This is 2 space here. Okay? Well, let's think about it this way.
I was looking at the picture.
Oh, no, the picture has nothing to do with this. Okay, sorry. That's just a slide I was using to write on. Okay. The first one starts at point 1, 0, right? When t is equal to 0, you're at 1, 0. The second one starts at 0, 1. And then as you increase t, this one goes this way, and that one goes that way. So basically, I think they flow the same direction. No, they don't. Because the second one starts there at X and is going this way. The first one starts here and is going that way. Okay? Because cosine t is increasing, sine t is decreasing. So the first one is going that way, and the second one is going this way. So they're going opposite directions. Okay? They're starting at different points and going in the opposite direction too. So 2 ways they differ. They're starting at different points and they're going in the opposite directions. As t increases from 0 to 2 pi, a point on the first one moves they say the second one first. A point on the second one moves clockwise, and a point on the first one moves counterclockwise. That's true, but they also start at different points and do it. Okay. So, that was 5. Number 6. I will need more room on this one for sure. All right. Which 3 of the following vector-valued functions parameterize the same space curve? So we're looking at 5 different vector value functions, but 3 of them follow 3 following. Parameterize the same space curve. Okay. The first one of these is minus 2 plus cosine t I plus 9j plus 3 minus sine t k. Okay. The second of these is 2 plus cosine t I minus 9j plus a negative 3 minus sine t k. C, which is not necessarily yes, is negative 2 plus cosine 3t I, which sometimes means yes, plus 9j. Y'all tell me if I'm doing right, because it's looking up and down that has me going crazy. Plus 3 plus sine t. Say again?
Minus
Oh, C, yeah, I had jumped down to D. My eyes had. Okay. Okay.
3T.
Say again?
3T on the.
Oh, that's a 3T there too. Okay. I thought these looked totally different because I was going down to D. Okay, this is minus 2 minus cosine T. I, that's yes. Plus 9J.
Plus 3. Yeah. Plus 9J.
Plus open parentheses, yeah.
Right.
3 plus sine T. Okay.
And then E.
Okay.
2 plus cosine T.
2 plus cosine T. I.
Plus 9J.
Plus 9J.
Plus 3.
Plus
3 sine T.
plus sine T. Yuck. Get out of there. Okay. Okay. All right. It says, which 3 of these 5 vector value functions parameterize the same space curve? Do you see one you can throw out right away? If I've got it written down right. Say again?
I'm gonna take a stab.
Okay, stab it.
C.
B. Why?
I said B. I said C.
Oh.
I didn't say
You said C. Want to throw out C because of the 3T in there?
Yeah, but I'm not sure.
Okay. We'll hold that in abeyance. It certainly looks enough different. You would think that would need to be out of there. Okay.
Well, all of them are 9 plus 9J except for B.
Okay, B. Okay, that's the one I was thinking you might pick out first. Because, let's just, actually it's a lot like this one. This is a 6J. This would be they all seem to be sort of circularly-ish, right? But this would be centered at 6. Let's assume that's a 9. The pluses, the minus would be one back here, minus 9. Couldn't be the same curve at all. Okay. Now, think. Did I get all the pluses and minuses right? Yeah, I think I did. Okay. The other thing is, these are all, except maybe C, the rest of them definitely are circles, right? And the thing is, if the center is at, for the X, is at minus 2, okay, this is minus 2, minus 2, minus 2, this is a plus 2. Now we already threw B out because it's on the, behind the plane, okay. Now this one, the center would be minus 2x, okay. This one's a plus 2, minus 2 would be back there, so the center would be in a very different place. So I would contend this one has to go 2, okay. But notice the center is the same on here, negative 2, negative 2, negative 2, 3, 3, 3.
But then you have a minus and a plus.
Okay, that just sends it in different directions, okay, and the 3T just sends it around faster, but it's still going in the same circle. Because you can think of this as cosine of u, sine u, okay. All the plus or minuses is changes directions like this. So I think it's A, C, and D, because those have the same center. The other two do not have the same center. So what do we say? A, C, and D, right? Let's see. A, C, and D. Fantastic. They got it right. All right. That finishes 13.1. Homework exercises here. Do any of the odds 1 through I think 1 through 15. But I wouldn't just do 1 or 2 of them. I'd do 1 of each group. Okay? Sort of. Then do either 17 or 19 or both. And then any of the, do 21 if you can, and do 23 if you can. Okay? Then do any of the odds 25 through 31. Then do 33. Then do any of the odds 35 to 43 and stop. Okay? Now, back up a little bit. Okay? I see a couple of things here. This is a hint. Viviani's curve? Who in the world was Viviani? Okay? That could be a paper topic. Or how did he develop this curve? That could be one. Or does it have any practical use at all? Okay? And they basically almost show you a practical use at all. Okay? So, anyway, there is possible paper topics there. Why am I saying this? I haven't gotten any papers in yet. And we're almost halfway through the term. So be thinking and planning and working on those. Don't put them off till the end. All right, let's look at further insights and challenges. I don't see anything all that great there, but you might see something you might want to pursue there as well. All right, now let's see. Yes, we're through with this section, 13.1. All right, let's go to 13.2. Well, I'd hoped to go to 13.2. It's just really not responding very quickly. Here it goes. I think it had fallen asleep. I think my computer had said he's just talking too much. So. I don't know, has the room gotten warmer, or is it just that I've gotten used to it? Huh?
I don't know.
Yeah. Well, I bet you that, yeah, that sun outside may be warming it a little bit. Okay. We'll go from current slide. Okay. Now. Yuck. Things jumping all over the place. Okay. In this section, we extend differentiation and integration to vector value functions. So this is called the calculus of vector value functions. This is straightforward because the techniques of single value variable calculus carry over with little change. What's new and important, however, is the geometric interpretation of this derivative as a tangent vector. We describe this later in the section. The first step is to define the limits of vector value function. Don't we always have to start there, huh? Okay, limit of vector value function. Vector value function R of t, that's a vector, R of t. It's really a vector function, well, yeah, okay. Approaches the limit u, which is also a vector now, not just a number, okay, as t approaches t0, if the limit as t approaches t0 of R of t minus u, the magnitude of that is going to 0, okay? In this case, we write the limit of R of t, vector R of some parameter t approaches t0, as being that vector u. Okay? All right. Now let's think about this geometrically. If we had this being vector r, there's the origin there going out here somewhere. Now, u, if it's some other vector, say here, then R minus U is in between these two, right? And that's not going to approach 0 as t approaches t0. Doesn't seem like, okay? Unless they happen to be R and U, to be like this, and as t approaches t0 being on U, then they line up so the difference between them is approaching 0. That's a terrible arm waving description that people at home can't see it, but best I can do in the thing. They don't really, well, yeah, they do. Here is their arm waving thing, and this probably is far better than mine. Okay. Here is your R of t, some value, any old value t, anywhere along that curve. And if this R of t approaches u as t approaches t0, in other words, R of t0 lining up right with R of t, then the difference between those is 0. Okay? The vector value function R of t approaches u as t approaches t0. Okay? Now they don't show what t0 is. So this is, say, t1, t2, t3, t4, t1. As t approaches t0, then R of t is approaching. Okay.
You are out.
And what's the time is it? Huh? Oh, is it time? Completely. I thought you were leaving early for your class. Okay. All right. We will start next time with Theorem 1. I think is the next slide. Yeah. We'll start with Theorem 1. We didn't get enough in here done for any new homework exercises, and I will do my very best to try to get the test finished, made up for next time. Chapter 12 test, I've got, like I was telling the others earlier, about halfway done. And as soon as I can get the rest of it. It's a really sort of tedious one to do because it has all these equation modes to get into, but I'll get it done. I'm just sorry I don't have it done yet. All right, we'll see you Monday. Have a good weekend. I'll see you tomorrow. Okay, and you tomorrow. I think any of the rest of you. Yeah, no, you're not. Okay. All right, good deal.